This week your experiment will be on the iodine clock reaction and the kinetics of this reaction. This is kind of a famous reaction for lab experiments because it's really neat to see the color change in real time when all of the ascorbic acid of your solution runs out and you form an iodine starch complex which causes a color change. And so I've drawn this to represent initially you have a clear solution. After some amount of time that will be used to determine the average rate of the overall reaction, you get your darkly colored solution, which could look black, dark brown, or dark blue depending on your solution itself, but ideally it should be a dark blue color when iodine binds to starch that you have in solution. And the kind of idea behind this mechanism of a reaction is that we have some concentration of ascorbic acid that we're starting with in solution, and this ascorbic acid decreases to 0, and once ascorbic acid runs out, our iodine is able to bind to the starch because the ascorbic acid reaction reducing iodine back to the iodide ion is a very fast reaction. So the concentration of ascorbic acid can be used to control that. What reaction we're really trying to look at the kinetics of is this reaction in green, hydrogen peroxide oxidizing our iodide into iodine. So all three of these are sort of interrelated in the system, but what we should think of is this hydrogen peroxide reaction, we'll call it R1 for the purposes of this lab. R1 is the rate determining. So we're going to look at the effects of the concentration of hydrogen peroxide and the effects of the concentration of iodide in solution. And this reaction produces iodine in its elemental form, I2. Now, as this is generated, it's reduced back into the I- form with whatever amount of ascorbic acid we have in solution. So at some rate, I2 is being formed, and we're immediately turning it back into I- so that this green reaction R1 can keep occurring. We'll call the ascorbic acid reaction R2. And we'll keep a constant concentration of ascorbic acid in solution so that the only thing we're modulating are the concentrations of hydrogen peroxide and iodide so that we can see their impacts on the overall rate of the reaction. So conceptually, our ascorbic acid is there to control sort of the stoichiometry of the overall time, and reaction 1 is what we're trying to look at the rate specifically for. So the rate should be directly influenced by the concentration of each reactant in that green reaction in R1. And once all the ascorbic acid concentration is used up and goes to 0, then we get our dark blue color. And that is when we stop our time. So when we see the color, that's our T final, and our T initial we will call 0. So that's what is happening in solution, but let's get a little bit more theoretical about what rates are conceptually. And so we'll talk about instantaneous and average rates and what impacts the rate. So an instantaneous rate is really just any single point along this curve. We could take a tangent line at that point and determine the slope of that tangent line. So it's an instant in time you can think about. The rate is the slope of the tangent line on that graph, or we could say the derivative. All right, the contrasting case is if we wanted to discuss the average rate, and in this lab we're looking more at the average rate. So we could select 2 different time points, and most likely we would select basically the initial time point and the final time point, which is what I'm going to do here, And these two time points are connected by a line. This line has a slope. So the slope of this line, rise over run, is our average rate. So slope of line between 2 points. So concentration of R final minus concentration of R initial over T final minus T initial, and that is our average rate, which if our T initial is 0, like we're starting at time 0 at the beginning, and if our concentration of R final is 0, we could set it up that way, and it makes it a little bit simpler, and we'll actually be doing that in this experiment. All right, so moving from there, the things that affect the rate, there are two main factors. We have concentration, and concentration affects the rate depending on the order of each reactant in a reaction. So let's just say we have reactant A reacting with reactant B to make C. The rate law that we could write for this reaction would be rate equals K times concentration of A raised to some power X times concentration of B raised to some power Y. The K value here is our rate constant, and it allows us to proportionally determine what the rate should be depending on the concentrations. Of course, brackets represent concentration of reactants, and the exponents are the order of each reactant, so kinetic order. And we'll use the method of initial rates to determine the order in this experiment. We'll walk through an example in a few minutes. But each reactant involved in a reaction as a part of the rate law will have its own order. The order could be 0, 1, or 2, and we will look at an example. The other effect that can affect the overall rate of a reaction is changing the temperature. And this actually impacts the value of K, the rate constant. And this rate constant is related to temperature by the Arrhenius equation, which looks like A, the frequency factor, times E raised to the negative activation energy over the ideal gas constant times T. So this equation is used to determine, essentially, if we can measure the rate constant at different temperatures, we can determine what the activation energy is, so EA, activation energy. And that is how we will apply it in this experiment. We're going to make our iodine clock reactions happen at a series of different temperatures and use the values of the slope and y-intercept to determine essentially what the activation energy is based on the Arrhenius equation. All right, so just a little overview of kinetics and this reaction. But let's walk through an example of the method of initial rates. So let's imagine I set up my reaction of A plus B makes C, and I run 3 different trials. The first trial involves 1 molar of both solutions. In the second trial, I cut the concentration of A in half, but I keep B constant. And in the third trial, I cut my concentration of B in half, but I keep A constant with my initial trial. And I measure the rate, which is the change in concentration over time. And for this, it's really an average rate because we're considering the total time from beginning of reaction to the end. So we can use this data to determine a rate law, which is really going to be us finding the values of the exponents, the orders of each reactant. And after we have done that, we can plug in and solve for the actual value of the rate constant using one of the trials. So it's a very useful tool to determine a rate law experimentally. And so let's walk through how we would figure out the exponents. So the key is going to be to look for, like if I wanted to know what the order of A is, I would need to look at which two trials are going to change my concentration of A without changing anything else. And so if I look at trials 1 and 2, B is held constant, A is changed. So that's going to be an ideal comparison of two trials. So if I take rate 1 and divide it by rate 2, that should be equal to the rate law of the reaction with the values from the table. So I'll plug in my 1 molar A, my 1 molar B, and then in the trial 2, 0.5 molar A and not 0.5, 1 molar B. All right, since B has the same concentration in both, that entire term I'll just go ahead and eliminate. And I can do the same thing with my rate constants. The rate constant should be the same because we are not changing the temperature. The only thing that did change is my concentration of A, so I will keep that term with its exponent, the unknown exponent, and I will also set them equal to the difference in, or the ratio of rates. So 0.20 molar per second over 0.10 molar per second. All right, so this is a bit more simplified, but we'll simplify it a little bit further. 0.2 divided by 0.1 is just 2, and 1 divided by 0.5 is also 2. So 2 equals 2 raised to the x power. If this wasn't super obvious that x should be 1 based on this setup, we could take the natural log of both sides so that we can take x from the exponent to be a factor in front of the natural log as one strategy. So natural log of 2 equals x natural log of 2. And we end up getting that x is 1 when we solve for x. So you can always apply that same mathematical operation, even though it should have been obvious from the very beginning there. So that means that our exponent for A, the reactant, should be 1. So I'll fill that in. All right, then we can move on to comparing rates for trial 1 and 3, because this is the point where we're changing the concentration of B, but not changing the concentration of A. So A was 1 molar in both trials, however B was 1 molar in trial 1 and 0.5 molar in trial 3. All right, and the rates were 0.20 and 0.05, so I can plug those in. 0.05. All right, so now that I've set that up, I can cross out my terms that are constant between both trials, and I'm left with just B equal to the ratio of rates. And so 1 divided by 0.5 is 2. 0.2 divided by 0.05 is 4. So if I want to pull my exponent, I can take the natural log of both sides like I did before, and I get natural log of 4 equals y times natural log of 2. And this leaves me with y, the exponent, is equal to approximately 2. So I'll plug that in here. So this means that A as a reactant is first order, and B as a reactant is second order. So if I wanted to solve for my rate constant at this point, I could. I could plug in maybe trial 1 data. I could say 0.2 is equal to K times 1 molar raised to the first power times 1 molar raised to the second power, and solve for a value of K. So that I will leave undone here, but you will need to do this in the experiment. All right, the last portion that I want to discuss is that part of this experiment, this will be likely the first time you've really encountered this in this lab, is a discussion of particular research questions that we're trying to answer with the experiment and how you can go about engaging in scientific argumentation about those research questions. So there are 3 separate research questions. We want to know the kinetic order of iodide in the oxidation step. We want to know the kinetic order of hydrogen peroxide in the oxidation step, so like our X and Y values that we just walked through in method of initial rates. And then we also want to know the activation energy of this reaction. And so we'll determine we'll use, to answer the first research question, method of initial rates, and we'll use that specifically for I minus concentration, so we can determine its exponent, and we would hold the hydrogen peroxide, wow, that's very ugly, sorry. H2O2 constant. All right, so that would be our strategy for figuring out the exponent for I. And then we also have the alternative. So in this case, we want to know H2O2, and we'll let its exponent be Y. And for this one, we'll hold I minus constant. All right. And so that's for research question 2. I should make a note of that. This is RQ1. For the third research question, we're going to want to know the activation energy. So if you recall, activation energy appeared in the Arrhenius equation as the numerator of the exponent. And in order to solve for this, we're going to actually have to make some sort of plot of our 1 over T, 1 over the temperature, and natural log of K. Once we have done that, this is related to the linearized form of the Arrhenius equation, which you can look up. Once we have, say, our 3 data points, let's imagine they make this kind of trend, you can get a line, best fit line, and use the slope and y-intercept to help solve for the value of activation energy and use that information to answer your research question. So when you do write a scientific argument, you have to develop a claim. So after you've done your analysis, you can say, essentially, the answer to this question is blank. Fill it in. So the kinetic order of iodide, let's say you get a value of 2 for X. You could say the kinetic order of iodide is second order. That would be your claim. You can support it with your evidence, which are your observations, your analysis, the calculations that you did. But then you're also supposed to support it with reasoning. And reasoning is where you go into maybe explaining how the method of initial rates even works, or what it means to be second order, how you know it's second order. What about your evidence led you to that conclusion? So these are important things to use when supporting your argument in order to really validate the position that you're claiming to hold based on your experiment. Now, what's important here is that you are consistent in your argument and it makes sense with what you actually observed, even if it doesn't actually make sense scientifically in this case. Now, you should be able to recognize, based on, your understanding of theory to some extent, when something makes absolutely no sense. Like if you got an order that is not 0, 1, or 2, you should be able to say that there must be some error present here and maybe come to some conclusion as to possible sources of error that led to that result. But this is not about getting the right answer. This is about logically arguing based on your own experiment. And so hopefully that's helpful preparing you for this experiment.